All right, good morning, everyone. Let's get started. So today, because today is a big day, election day, so I plan to end the class a little bit earlier, if you agree. So maybe yeah. So today we're gonna end the class about like 10:45 or 10:30 or something like that. Yeah, because it is stressful today for everyone. All right. So so let's get started. So I'm gonna stop the video, my video, to save some resource. And okay, let's get started. So as I mentioned, so today is the election day. So we plan to end the class a little bit earlier, like around like 10:30 or 10:45. So okay, this is our plan. All right. So last time we so last in the last week we learned how we can use um, um, the linear model to help us detect the major gene effect, right? So okay, so today we're gonna continue this topic, and we're gonna talk about the F2 design. So because this is a F2 design, um, so it's better than backcross because we have data for all three genotypes, right? So that means like either the midpoint, the additive effect, or the dominant effect. All of this can be estimated using your data because we have all the uh, data for three genotypes. All right, so then we're going to use this multiple regression model. So when we say multiple linear regression model means we have a single response variable, but we have more than one predictor variable. Okay. All right. So obviously, give me a second. So let's see. Ryan cannot join the meeting. Let's see. So he has problem. Okay. Passcode. Okay. Let me send out the. Um, all right. Give me a second. Sorry about this. I think Ryan has some problem logging in. Let's see. How can I do this? Oops. Sorry about this. Give me a second. So let me. Hmm. So back meeting. I think we. Let me copy. So in the syllabus, we have the information about the meetings, and let me send this information to him and see if he can get this. Ryan. Okay, done. Okay, sorry about this. Let's continue. All right. Where's this? Sure. Okay. Okay. All right. Okay. So All right, so we are talking about the F2 design, right? So in F2, so this is a very beautiful feature for F2 design. So because when we talk about a single locus, 3 genotypes here, and the ratio is beautifully designed as 1:2:1 ratio, right? So in this case, we can use two random variables, Z and W, uh, to help us to develop the linear model. One is used for the additive effects. The other random variable is used for the dominant effects. So because only the homozygous individual has the additive effect, so that's why you see the +1 and the -1 here, right? For the heterozygous, there's no additive, so 0. But for the dominant effect, so only the heterozygous genotype has the dominant effect, but not the homozygous. So that's why, so usually in a conventional way, we put 1 for the heterozygous, but 0 for the homozygous. So this is uh, how we design this model, linear model. Okay. All right. So we have learned how we can use the least square analysis to help us to estimate uh, the additive effects in the backcross design, right? So in here, when we deal with a F2 population, we still can do that using the least square questions. I heard some noise. Do you have any questions? Okay, no? All right. Oh, I saw Ryan. Okay, good. So now you made it. Okay. All right. So okay. So the same. So when we deal with the F2 population, we still can use the least square. Hopefully, you still remember what the least square means, right? All right. So we use the least square analysis to help us to estimate the regression coefficient here. So we have one intercept, which is B0, equivalent to mu, right? And B1 equivalent to the additive effect, and B2 equivalent to the dominant effect. All right, now we have 3 random variable. Actually, the first random variable for the intercept is always equal to 1, so it doesn't matter. But for this two, so 1 is Z, which is used for the additive effects, and the other one is W, which is used for the dominant effects. So this is the clear form solution for these 3 regression coefficient using the least square estimation. And yeah, this is the complete form. And also we can estimate the residual error, the variance of the residual error. So this is how we calculate this, because last time we mentioned, because here we have a model with 3 parameters. That means when you use the data to estimate these 3 parameters, you're gonna lose 3 degrees of freedom, right? So the total number of data points is n, but you lose 3 degrees of freedom. So finally, for the residual error, so there are only n minus 3 degrees of freedom. So this is how we calculate the residual error variance. Okay, any questions here? Okay, perfect. All right, now, so once we got the B estimation, so this is from least square, right? And we can also calculate the variance of this estimation, so variance B. So why is that? Because because we want to construct a test statistic. So last time we talked about in engineering major, so they try to detect the real signal by constructing a signal noise ratio. But in statistics, the same, we construct a statistic. statistic, which is also defined as a ratio, but here the numerator is the thing we want to estimate, want to test, but the denominator is the standard error for this estimation. So this is the test statistic we want to construct in statistical hypothesis testing. And that's why we want to estimate this and this, right? Because the square root of this variance of the B estimation is the standard error. Okay. And once we have this, so we can easily construct a F test, F statistic. So this is the statistic we want to construct. So if you look at this F statistic, it's clear this is a ratio, right? So the numerator is the thing to be estimated from your data. And this is the denominator if you see the -1 here, because this is, yeah, -1 means the inverse. So you're gonna see the ratio here. Is that clear? So this F is a statistic test. This is a statistic we want to construct to test the estimated gene effect. The B1 is the additive effect, and then the B2 is the dominant effect. Because we are testing both simultaneously. So we're going to construct a F test with the first degree of freedom equals to 2, and the second degree of freedom is n-3, which means like the total data point minus the number of parameter you estimated from the linear model, right? And this is the significance level we would like to use for this test. So usually we're going to talk about this in a minute. So because the degree of freedom equals to n-1, if n is large enough, so if we have sufficient number of data points, so this F statistic can be approximated to a chi-square test. Okay. All right. This is only true if n is sufficiently large. Okay. So so in the case if you do not want to test both, for example, you are only interested in the additive effect, or if you are only interested in the dominant effect, you can just use a simple F test to test that. So in that case, you only test one effect, then the first degree of freedom equals to 1, but the second one is the same. Any questions?
I have a question.
Yes, please. Yeah, Livy.
Can you go to the previous slide?
This one?
Yes.
Okay.
Where is the 1/2 coming from?
One, well, I'm sorry, where is what?
The last line, it says F equals 1 divided by 2.
Oh, okay, sure. Let me clear the slides first. And yeah, so this involves some calculation. So this are, so we're going to talk about this a little bit later, but now, yeah, since you asked this question, so this equals to rank of the matrix here. So the matrix here, the rank equals to 2. So that's why you're going to see the number here. If the rank of the matrix equal to 3, for example, if you want to test the B0, B1, and B2, so this number becomes 3. So that's the rank associated with the matrix. So we're gonna come back to this point a little bit later. Yeah, good question. Okay.
Thank you.
Any other questions? Okay. All right. So now, so for publication or teaching, I think yeah, matrix notation is a better way because it's more clear and neat. So for example, if we want to test the additive and the dominant effects simultaneously, we can always use this vector, and we can use a design matrix here to help us to develop a contrast. So if we want to test this two, if you multiply this two matrix here, so this is 2 by 3, this is 3 by 1, so 2 by 3, 3 by 1. Then if you multiply this matrix, you will get a 2 by 1, right? So that's this. So, okay, now if you want to just test the additive effect, you use a simple matrix here. This is also a design matrix. If you multiply this matrix with this one, the same one, you're gonna get a simple B1, right? The same thing here. So we always use the vector, the full vector of the 3 parameters, but we can change the design matrix to help us to identify the things we are interested in testing, right? Okay, now, so suppose we want to test the B1 and the B2 simultaneous. Now the variance of this linear combination here is this. This is how we construct the variance of the estimation for B1 and the B2. Now, if we want to just test the B1, so the variance of the B1 estimation equals to this, the same form, but using different design matrix here, right? Is that clear? Mm-hmm. So it's much nicer to express this kind of calculation using matrix notation. But don't worry. Let me think. So maybe, yeah. This is simple matrix notation. I think every one of us should understand this. And probably in the final exam, I'm going to give you some very simple version of this to test you how to construct a test. For example, using the matrix notation, how you can construct a test to test a single B1 or B2 or both simultaneously, right? So don't worry, I'm going to give you some practice test practice questions to make sure you understand and you feel comfortable about this kind of questions. All right. Any questions here? Okay.
I have a question about the B. Like the variance is, if there is 2 parameters, then the variance is 2 by 2 matrix, right?
Yes, that's right. So that's a good question. So for one parameter, that's easy, right? Because variance is also a scalar. But if we want to calculate the variance of 2, so the diagonal element, so usually it's the variance of each parameter itself, B1.
Yeah.
And here, variance, oops, B2 here. But the off-diagonal element is represented the covariance between these two. Okay, the same here. Is that clear? 2 by 2.
Yeah.
Mm-hmm. Yes.
So
Very
for
good.
L, we also use like the B1 for the L matrix. It's also 0, 1, 0, and looks like.
You mean here?
Yeah.
Yeah. So that's right, because we use the very so for each element, that's the binary, so either 0 or 1. So using this simplified design matrix, we can generate the linear combination of the 3 parameters, and we can construct anything we want to test.
Mm-hmm.
Okay, good. Very good question.
Well,
other questions? Yes.
Professor, why have we taken the separate rows from each vector representing B1 and B2? And
Say that again. I'm sorry.
we've deconstructed the matrices and put them into single line vectors in the second grouping of numbers and equations that we have on this slide. Why do we do that?
Oh, yes, because sometimes so this is the full version. So by doing this only, so you can get everything you want. But sometimes you don't want to test them all because you are only interested in B1, right? So you just, yeah. Right.
I get it.
Mm-hmm.
Thank you.
Sure. So yeah, if you just do this, you can get information for both of this. So just and the extra, you can get extra. But sometimes, yeah. So based on your experience, you don't think like if you don't think the dominant effect is relevant at all, so you can ignore the complicated calculation. Just jump to the second step using the simple calculation to test the additive effects itself. Does that make sense?
That makes sense.
Okay, good. Okay, so the rank. Let's go back to the question, the Nivi's question. All right. The rank. All right. So when we have a matrix, so usually we want to calculate the rank. The rank is defined as the rank of a matrix is defined as a oops. No, sorry, not yet. So let me see if next. Okay, so this is the rank. Okay, so the rank of a matrix is defined as the maximum number of the linearly independent columns, vectors, or row vectors in the matrix. And the maximum number of the linear independent rows, yes, okay. Both definitions are equivalent. All right, so I don't want to spend too much time on this because so it's not that complicated, but it takes time to explain. So I hope I believe most of you have already learned this when you study the college algebra. But if in case your background in this area is not that strong, so please, yeah, take some time when you have time. So take some time to review the slides and also find some useful information from website, internet, and help you to understand this. So this is the definition for the matrix rank. And here, because when we talk about the design matrix, right? So there's a rank. All right. So each design matrix we can get a rank. For example, for the dominant effect, only that design matrix, the rank equals to 1, and so is the dominant design matrix, also 1. But when we want to test a B1 and B2 simultaneous, that matrix, do you still remember that? So that matrix is something like this. That matrix, the rank is equal to 2, right? So overall test, the formula is this. So that's why you see a 2 here, right? Rank. But when we tested the additive effect only, so this becomes 1. So you do not see this ratio. And the same here, you do not see this ratio. It's 1. So that's why when we want to test the B1 and the B2 simultaneously, we see a slightly different formula here because of the R, the rank. All right, any questions? Okay, so as I mentioned, when you have sufficiently large data points, in another way, so if N is extremely large, so we often use word test statistic rather than the F test. And this is the relationship between the OR test and the F-test. Also, R here is the rank of the design matrix. And if n is sufficiently large, so we use OR test, which is a chi-square distribution, and so then we can use chi-square distribution table to help us to find the critical value and the p-value and help us make the final conclusion in terms of the genetic effects for a locus, either the dominant effects, or either the additive effects or the dominant effects. Is that clear? So I try to build. So we try to learn some new stuff, which is based on the knowledge we learned before. So we try to develop a strong connection between the old knowledge and the new knowledge. So is there any problem for me to migrate you from the old knowledge to the new knowledge here? Any connection lost?
Yes, a little bit. So we're going from, so the Wald test.
Yes.
That is equivalent to an F test, considering if we could take rank into consideration.
Not the rank. Rank is always there. So because here we have several different numbers here. So the rank is associated with how many parameters you want to estimate. So we use M. M represents the parameters, right? So here, if you want to test the B1 and the B2, then M equals to 2, right?
Mm-hmm.
So this is the rank. This number is different from the N here. So N here is the how many progeny you got from your F2 design. So data point. So suppose you produce 100,000 progeny from your F2 design. So then N equals to 100,000. So that's a big number. That is considered a big number, sufficiently large. In that case, so when we talk about the F test, right? The F test, there are 2 degrees of freedom. First degree of freedom is the same here, R, the rank, and the second degree of freedom equals to N minus R, right?
Mm-hmm.
Do you still remember? So this is the F distribution. However, if this N goes to infinity, then this thing is gone. We only consider this, and this becomes the chi-square test.
So R is the freedom of the chi-square test?
R, no, R here. So for example, so if we just test the dominant effect, R equals to 1, right? Because that's only one thing we want to test. But if we want to test the B1 and the B2 simultaneously, R equals to 2, right?
Mm-hmm.
Right? Yeah, that's the number of parameters you want to test. But here, oh, no, sorry. In this case, N minus 3, not R. Sorry about this. Because here, R equals to 2 because we want to test the B1 and the B2. But how many parameters have we estimated from the model? 3, right? We estimated B0, B1, and B2. So the degree of freedom for the second one, in F, we have 2 degrees of freedom, right? D1 and the D2. And this is the significance level. Okay, so the D1 is always equal to N minus 3 in F2 design, right? Because we want to estimate B0, B1, and B2, right? But here, the D1 could be 1 or 2, depending on how many genetic effects you want to test.
Okay, so no matter how many parameters we are testing, the freedom of the chi-square is N minus 3.
No. You mean here?
Yeah.
No, this one, the freedom of the a chi-square test is associated with the number of the parameter you want to test. So if you want to test, so what test, let's say, what test, if you want to test the B1 only, which is additive effect, right? So in this case, chi-square test, degree of freedom equals to 1. If you want to test the B2, the same, chi-square equals to degree of freedom equals to 1. But you want to, if you want to develop a what test, which is a chi-square test, want to test both B1 and B2, then this becomes 2.
Okay.
Good question. And so I hope it's clear. Is that clear?
Yeah.
Okay, good.
But how is this connecting to chi-square? We have the Wald test, which is equivalent to the F test. And then
yes.
all of a sudden, you're bringing up chi-square.
All right. So, okay. So what test is not a, is a test. So what test is a way that we construct a test statistic, right? And the test statistic of what test is a chi-square distributed random variable. So, I don't want to say what test is the same as chi-square test. I think I think I can say what test is one of the chi-square test. So chi-square test can include multiple situations, including what test.
Okay.
So if you construct a what test, so we're going to talk about what test. This is a way you can use your genetic data to construct a test statistic. And once a test statistic, what test statistic has been successfully developed, that statistic is a random variable, which is chi-squarely distributed.
Okay. Okay.
Does that make sense?
A little bit more. Yes.
Mm-hmm. All right. I know, yeah, this is tough. This is tough. So to better understand this part, I think, so maybe I can find some reference link and post that link to the iLearn announcement. So when you have time, you can study by yourself to learn the connections between different standard commonly used distributions. So first, we are very familiar with the normal distribution, right? The standard normal distributed random variable, which is centered by 0 and with the standard deviation equals to 1. So that's the standard normal distribution. And starting from there, so we can see how this standard normal distributed random variable can be connected or can be associated with other distributions, for example, chi-square distribution, and how a chi-square distribution is associated with the F distribution, and so on. Yeah. It is hard. Yeah. Any other questions? So let me take the notes. So I'm gonna find some reference, more interesting stuff for you to read. I hope it will be interesting. It will be fun to read. Connections between distributions. Okay. Yeah, this is my homework. I'm gonna do something for you. The extra additional reading material. All right. So any questions so far? So anything I can help understand? No, go ahead. All right. So this is the rank. And okay, now scale of the genotype indicator. So we have learned this, right? Because for F2 population, we can use this multiple linear regression model to help us describe the relationship between the phenotypes. and the genotypes. So here we use two random variable indicator to to represent the genotypes, which are associated with the additive effects and the dominant effects. So this is how we define this two random variable, right? All right. Okay. No problem here, right? So this, yeah, this is very, very important, very basic thing. Don't be confused in here. Otherwise, yeah, there will be a problem. Okay. Now, so this is what we have learned. So this is the linear model. And the expectation of the linear model is this, right? So basically, those are the parameters. They are constant. We don't know this, but we know this is the constant. We want to estimate this using our data. But the expectation is relevant to this because we have two random variables here. So the expectation will be reflected here. All right. This is the expectation. And this is the variance of y, because we have two random variables. So we need to calculate the variance of these two random variables. Because z and w is independent from each other. Why is that? Because the covariance between z and w is 0, right? And this is due to the way how we define these two random variables. So we can prove the covariance between these two equals to 0. That's why we do not see the covariance here. Okay. And this is how we calculate the variance of the whole thing. Any questions here? Good. All right. Now we will look into the different scales of the genotype indicator. So this is the original way we define the X matrix, right? So the 1 is for the intercept, the B0, so it's always 1 there. But we have Z for the additive effects, and we have W for the dominant effects. However, in some situation, we want to test something different, not using the original designed, sorry, this is Z, typo. We are not interested in the originally defined Z or W, but we are more interested in another variable, which is a linear combination of this Z. So this is a factor, CZ, a constant multiplied by Z, and CW, a constant multiplied by W. All right, which means like we use a different way to design our linear model random variable matrix. All right, so if we define X star using this linear combination of the originally defined random variable, then so let's look what happened here. So this is the original linear model, right? Once we define the X star, so we're gonna rewrite this model in this way. Now the B also changed compared to the original B, because B equals to this, B star. Any questions?
What does the 1 indicate again?
You mean here, right?
The first line?
The first line here, right?
Mm-hmm.
Okay, sure. So when we look back, so let me clean this slide first and then go back. So, okay, so this is the linear model, right? Okay, we know before the additive effect, we have a Z variable, right?
Mm-hmm.
Before the dominant effect, we have a W variable, right?
Yes.
But the same, before the mu B0, we also have a random variable, but which is not a random variable because it is always equals to 1. So that's where 1 comes from.
Okay.
So if we use the matrix notation, so we can use this, the same thing. This linear regression model is equivalent to this. We can write this into X matrix plus times B.
Uh,
And now B equals to what? B equals to a vector here. Oops. Equals to a vector here. B0, which is mu, right? B1, which is additive. B2, which is the dominant, right?
mhm.
And the X matrix becomes what? Becomes, this is 3 by 1. And the X should be 1 by 3. Then if we multiply this, this will become a single value, right? Scalar. Okay, but what is here? So we have 1 here, and we have Z in the middle. We have W here. Is that clear?
Yep.
So yeah, only these two can change in terms of the genotype, but we just treat this as another random variable, but it stayed the same. So that's why 1. Yeah, very good question. Yes. So that's why we see this, right?
Oh.
Does that make sense? Mm-hmm.
Yeah, that makes
Okay.
sense.
Yeah, sure. So this means what? This means we can arbitrarily change the way we define X. This is Z actually. So I'm going to show you. So you can define Z as 1, 0, minus 1, and W as 0, 1, and 0. But you can change in some different situation arbitrarily. So that's why we can put the constant here before Z and W. But if you want to change the scale, so then this is the relationship between the original linear model and the model that you change. You use the change the designed Z or W, right? Okay. So when we want to estimate this B star, the same thing, but in different scale because you change the scale, right? And so for the new linear model, you have a slightly different B. So the B star is actually related to the original B, but with a coefficient here, right? Okay. Now, once you can estimate this B star, so you also need to calculate the variance of this estimation because of what? Because we want to construct a signal and noise ratio, which is a statistic test, right? Okay. And this is how we do this. So once we want to test this B0, whether B0 equals to 0 or not, so we use the same definition to construct a F-test, but guess what? Eventually, you come back to the original test. So the same, which means like, so this is the same with, this is the same statistic you end up when you use the original scale to do the test, which means if you change the scale for defining the Z variable and the W variable, it will not change your test results the same. This is the beauty of the linear combination, which means, yeah, in any design, you can arbitrarily using different way to design your Z variable and the W variable for the dominant additive and the dominant effect, but this change will not affect your statistical testing.
Could you explain that logic again? The beauty of the linear recombination.
Yeah, sure. Okay, let me show you. Okay, so this is tough stuff, but yeah, hopefully, yeah, we just keep slow to keep the slow pace to make sure everybody feel comfortable with this concept, because this is very important, very important. Okay, now this is how we define the original linear model, right? We use Z equals to 1, 0, or minus 1 for 3 different genotypes, right? We use W to represent the dominant effect, 0, 1, and 0. So do you agree with me currently?
Yep.
Okay, good. However, if you don't like this way, so you say, okay, I want to define the Z in a different way. For example, if we want to define like 2, I want to define 2 as the first genotype, still 0 here, but -2 for the second one. But for W, we want to say, okay, maybe still 0 here, but I want to say this is 100, because for some reason that can help you to interpret your problem easily in terms of the biological knowledge, okay? You want to use this scale to code your data. Does that make sense? So we say this is Z star.
So regardless of scale, we're good.
Right. So even you
come
use
back to the
different
original equation.
Yeah, unless as long as there's a linear association between these two. So as you can see, the Z star is actually equal to 2 times Z, right? And the W star is equal to 100 times W. Is that right? So here the CZ equals to 2, right? And the CW equals to 100, right? Which means you use your own way. So everybody may prefer different like scales to define these two variables. But when you come to a test, so they are equivalent to each other. So even you use different way to design your two random variables, so finally you get the same conclusion if you want to construct the F-test to test the genetic effects for B1 and B2. Does that make sense?
Yes.
Yeah, why is that? Because of this proof. Okay. Yeah, this is proof. So you finally, yeah, so following this, using the different scale, and so then you're gonna estimate different B star, but finally you end up with the same equation like before. Okay.
So will the F statistic value be same for just 1, 0, -1 and any other linear combination?
Yes. Yeah. If you don't believe, you can test. Yeah, they're the same. Yeah.
Okay.
Because there exists a linear association between the new variable and the original variable, right? So, yeah. So finally, you're gonna get the same test statistic. So we'll not change the conclusion. This is a beauty. So that's why. So if you want to develop your own data, you can define your random variable at your will. So sometimes so you can find a better way to define this random variable to make your calculation much easier, something like that. So this is a very, very nice feature for this. Okay. So, okay, let's move on. All right, so I think let me. What time is it now? So, let me like let us like spend 10 more minutes. Then we're gonna end this class. Is that okay? Okay. All right. So this is the standard form, right? So when we use the original designed Z or W, so we can calculate the variance for Z in the F2 population, which is 1/2. And for F2, this is F2. So the variance for the W equals to 1/4, and the covariance equals to 0. So this is, we have covered this before. This is important. So I may ask you to prove this for me, yeah, in the final exam. But it's easy, so you can find this place and see how to prove this, right? Okay. And so now the variance of the the total variance of the phenotype should be the sum of these two components, right? So the one component from the additive effect, the other is from the dominant effect, and the covariance here. But covariance equals to 0, so this term is gone, and only leaving these two terms here. So one is here, one is here. That clear? So this is very nice in terms of biological interpretation, beautiful, but not that attractive in terms of computational convenience. So this is very easy to understand, and it's easy for me to teach this class. But when you want to develop some R code to do the calculation, this is not very nice. So that's why we want to use different skills to help us make the calculation much easier. So that's why so I mentioned that feature. So if you use different design, the z variable and the w variable, it will not change the conclusion from the test, but it will make your calculation much easier. Does that make sense? Okay, so for example, this is a way to design, another way to design the z variable and the w variable. However, so because this is a F2 population, so we want to construct the z variable and the w variable in a way that these two are orthogonal. Orthogonal, this is another term, orthogonal, which means they are independent from each other, something like this, orthogonal, independent from each other. And when this is true, so you still can get the feature like this: the expectation of z equals to 0, and so is the expectation for the w. And also another very beautiful feature for this design is like the variance for both z and w equals to 1. This is very standard, beautiful design, right? So if you use this kind of way to design your z and w variable, and the same, you can, okay, probably this is a good question that I can put on the exam. So please show me this for a F2 population. This is only true for the F2 population because of what? Because of the beautiful ratio, right? So the three genotypes, the ratio of the three genotypes in this F2 population equals to 1/4 versus 1/2 versus 1/4. So based on this feature, these are true. And why is that? Please prove this for me. So this is a very good example. Because I don't think I have. Yes, okay. I don't give the derivation for this. So, but you can refer back to the derivation when I use the standard definition for z and w variable. Does that make sense?
So we write a proof because the ratios of the progeny in this of the F2 population equate to 1/2, 1/4, 1/2.
That's right.
And that pretty much gets approximately to 0.
Yes, yes. So yeah, that's intuitively, yeah, that's right. But I will ask you to mathematically prove this. So for example, if we want to prove this, EZ, so EZ so you have to use the formula, right? The EZ equals to what? To the summation of genotype. There are 3 genotypes, right? The genotype variable times the zi and times pi, right? Okay, now summation of this, what is that? So first you have square root 2, but times 1/4, right? Plus 0 times 1/2, right? Plus minus square root 2 times 1/4. So what is this? This is 0. So bingo, you proved the first one. So you need to do this again, and this, and this. Something like this.
So we just proved it for Z. We need to do it. We need to do the same for W.
Yes, yes. So you just find the right formula to calculate this, and to show me, okay, this equals to 1, and the covariance equals to 0.
Okay.
Good. All right. So don't worry. So this is an easy example, right? And I always like put the question like this simple on the final. So my purpose for this class is I will teach you a lot of good stuff, the solid knowledge, which will be hopefully very useful for your future. But for testing, I do not make any like tricky, like confusing questions to show how interesting this topic is. No, I will not do that. I just want to use very basic thing to test if you understand the basic knowledge, basic logic behind. So yeah, that's the key point for this study. So sometimes, yeah, it is. You will find it is very hard to understand most of the some of the stuff, but you will find it is much. But if you spend time, efforts on learning this, and once you understand this, you will find the final exam is so easy to finish. So
I have a question for the W. So
oh, you mean the linear combination, right?
yeah.
So this is another. So
Linear.
yes, but
it's
still, so if you see W equals to 0, 1, 0, but this W is not a clearly linear combination of that, right? But so I just want to say, if you use linear combination of this will not affect your test. But sometimes if you use a non-linear if you use a different way to define W, but which is not linearly related to this one, but if this design still meet the criteria of like these two random variables are independent and they are the expectation of this equals to 0, still, yeah, this can make the same test results. So does that make sense? There are two things. So first, if you use W and and then if you use a different W, which is the linear combination of W to do that, W. So this will not affect your test. But if you choose another W, which also meet the criteria like Z and W are independent and they are centered by 0, the same, yeah, this is another situation you can get the same test results as well.
Okay.
So in statistics, there's a way like it is necessary but not sufficient. Let me think, something like this, or the other way. So yes, if you use a linear combination of the original W, you will definitely get the same test. But that's not the only way you can get the same test.
Okay.
Yeah, you can have some other defined W, which is not linearly related to your original W, but still you can get the same test. Yeah. Okay. Good question. Yeah. All right, so I think I'm gonna stop here because this will be another very difficult topic. We're gonna save this one for the next time. And any questions so far before I dismiss the class? I know today is a big day, stressful day for everyone, so that's why yeah, I'm gonna end the class a little bit earlier to make each of us a little bit easier. Any questions? Okay, so if you do not have any questions, we're gonna stop here, and hopefully you will have a happy election day. Bye bye, everyone. Bye bye.
Bye.
Bye.